Hey everybody, and welcome back to Fermi Physics Solutions. Welcome back to the second video in the concept explainers. And this one is again following on from the first video of looking at a electric current, in which we described how charge particles flow around the circuit based on potential difference. This video is actually going to look at the concept of what current is itself, so it's going to be really short. So just to review, in the last video we saw that current flows from the positive to negative terminal. So we say that the conventional current goes from an area of high potential to low potential, where high is the positive and low is the negative. Remember, this is conventional current, and later on we can look at the concept of electron flow, which is the charged particles themselves, which has a slightly extended version and a slightly different way it slightly behaves. So keep in your ideas that the charged particles are moving, in this case, in the counterclockwise moment from positive to negative. So here's what we're going to do. We are going to pretend we're putting a little counter on the wire. It's just a little tiny loop, and the loop is perpendicular to the wire. So basically any charges that go through it, that little crosshairs that we can see represents a perpendicular plane inside the loop, and it's perpendicular to the wire itself. The idea basically being we're just going to count the amount of charge that passes here in 1 second, because that tells us what current is. Now the important part is you are not counting the amount of particles, you are counting the charge that goes through it. So the overall charge for all the particles that pass through it in 1 second. Just for this video, I'm going to make it really simple. We're going to say that one particle with a positive on it has a charge of 1 coulomb. But the important part is that we're always thinking in terms of how much charge is passing through the loop, not how many particles. Just for simplicity, I've made the diagram so that one particle has 1 coulomb of charge. Realistically, you need trillions and trillions of charged particles to move through your loop to get your 1 coulomb. But just for the sake of the diagram, it's easier. So if we look at this diagram here, this would just be kind of a close zoom up. Here we can see that there are, going through my loop, there's 3 coulombs. So if there's 3 coulombs going through that loop in 1 second, I would call that 3 amps. I'm representing that with 3 particles. Realistically, I would need billions of particles to make the 3 amps passing through the loop in that 1 second. Again, in this representation, I can see that there is 4 coulombs passing through the loop, so that means that there is 4 amps of current at that particular point in my circuit. The next diagram, we can see that there is 6 coulombs passing through that loop, so that loop represents that there is 6 amps of current at that particular point, because there is 6 coulombs passing that point in any given second. So if I were to draw up my diagram and I were to take a snapshot of the charges moving around the circuit, so this is a frozen moment in time, we can see that all those charges move in a counterclockwise direction as denoted by the red arrow. And if I apply my loop to that arrow at a given point, you can see that there is 3 coulombs passing through that loop, which then tells us that at that point in the circuit there's 3 amps, because there's 3 coulombs passing through that point per second. What I also know is if I put a loop here, an identical loop, I can also see 3 coulombs passing that point in a given second, which means there's also 3 amps at that point. If I put it here, I can also see there's 3 coulombs passing through that point in a second. That means I have 3 amps there. In fact, if I were to put an identical loop, I know I've made the size bigger for the diagram, just for visibility, but if I were to put an identical loop going through the center of the battery, and I take into account that it's an electrochemical reaction, I would actually find 3 coulombs per second passing through the center of the battery. What this tells us is that current behaves as a constant model, or as a constant flow going around the whole circuit. There is 3 amps inside the battery, there's 3 amps in this wire on the left, there's 3 amps in this wire in the bottom, and 3 amps in this wire on the right hand side. And as long as the chemical reactions inside the battery keep going, you will have 3 amps circulating that circuit until the battery becomes spent. Just a quick note, never set up a circuit like this. because you'll have little to no resistance bar, just what's there in the wires, and that can cause your battery to overheat, and possibly the casing can get damaged, and you could have the battery leaking some of its internal acids or metals, which could be very, very dangerous. So never set up a battery where you connect the positive to the negative directly, because that can lead to bad things. So what I noticed here is in our circuit, like, we have 3 amps at every point, but when you actually set up an electrical circuit, this is not what you do, because you can't see the charged particles. So we then put in what's called an ammeter instead. And if I put in the ammeter at each point, well, as we saw that there was 3 coulombs per second passing at every point, which means that every point in this particular circuit, there's 3 amps, and the ammeter placed at any one of those points will still record 3 amps for me as well.